Hello everyone. Today we'll be talking about degrees of freedom in an orthogonal factor model. You might remember that since we introduced the factor model, I've consistently been saying that generally we have approximate solution. We don't get exact solution. And in the last lecture we also discussed how a given solution can be rotated in order to get multiple solutions. Okay. So today we will see under what scenarios can I have an exact solution or maybe approximate solution or multiple solutions. Okay. So that's where this concept of degrees of freedom comes into picture. You might have studied degrees of freedom in your undergraduate course. For example, when you talk about say chi-square test, say chi-square test for goodness of fit or independence, you know that degrees of freedom has to do something to the number of parameters in that model. So the concept in factor analysis is equivalent. So we try to estimate the difference between the number of parameters in the old model, where old model would mean no factors, all the original variables, and number of parameters in the new model, where new model will be the factor model, which is supposed to have reduced dimension, and that difference would be degrees of freedom, because that would tell me how many extra parameters did I have in the old model or how many less parameters do I have in the new model. Okay, so let me introduce it more mathematically. So what is our model? Our model is x equal to qf plus u plus mu. This is our model, and you remember the orders. X is p cross 1, q is p cross k, f is k cross 1, this is p cross 1 and p cross 1. Okay, so in my original data I have x as p cross 1, and from that x we try to estimate sigma, which is of order p cross p. Okay, so when I say I'm going to estimate sigma, which is of order p cross p, how many entries do I have to estimate actually? So my sigma matrix is, we know, a symmetric matrix. So I have to estimate this diagonal, of course, variances, and then maybe these covariances. Okay, so either the upper triangle or the lower triangle, because it is symmetric, we have to estimate only one part. So suppose I estimate only lower triangle. So how many total entries are there? Can you think? Okay, see, I have one entry here, then 1 and 2. So one entry coming from this, then two entries from this slanting line, then 3, 4, 5 up to p entries. So basically I have 1 plus 2 plus up to p, that is p into p plus 1 by 2 distinct or unique entries that need to be estimated. Okay, so this in an original model without factors, or so-called old model. Now in factor analysis we are supposed to reduce the dimension, so we are representing the p variables by k factors, where k is supposed to be much less than p, and hence it is expected to reduce our work. So we are expected to get less number of parameters. So how many parameters do we have, that we have to check. Now the thing is, we know that what we have to do is we have to express this sigma as q prime plus psi, where q is k cross p, so q is p cross k, so q transpose would be k cross p, and then this is p cross p, and we know that this is diagonal. So from psi only p entries need to be estimated, others are anyway constrained to be 0. From q all p into k entries need to be estimated, because q is not a square matrix, so no question of symmetry, etc. So p into k entries from q need to be estimated, p entries from psi need to be estimated. Okay, and people say that actually even this is not enough. Why? Because with this I still have a large number of parameters at my hand. Okay, so pk plus p, this in itself is like a pretty big number. Okay, is of course greater than 2p. So people like to put some additional constraints in order to further reduce the number of parameters. So what are the additional constraints that you can put? So generally the constraints that are put are q prime psi inverse q should be a diagonal matrix. Okay, so we know psi is a diagonal matrix, but we go one step ahead and say that q prime psi inverse q should also be a diagonal matrix, or instead of this some people say that q prime d inverse q should be a diagonal matrix. Okay, q prime d inverse q should be a diagonal matrix. Now why what would be the reduction? So normally what is the order of q prime psi inverse q? So again q prime is of order k cross p, this is p cross p, and this is p cross k. By the way, D you know is a diagonal matrix whose diagonal entries are variances. Okay, diagonal matrix whose diagonal entries are variances of xi's. Okay, variances of xi. So originally q and q prime psi and d are diagonal matrices, but q is not a square matrix, so we don't know anything about q. But in this way we try to impose some constraints on q. So overall the matrix q prime psi inverse q or q prime d inverse q is of order k cross k, and we want to make it diagonal, means we want only these entries to be non-zero, everything else is 0. So how many constraints do we put? And secondly, are all these constraints distinct, or is it like a symmetric matrix? So first let me check that. So what do I know about q prime psi inverse q? So q prime psi inverse q, if I take prime of it, then that would become q prime psi inverse prime q, psi inverse prime, and then q prime prime. So this would be q prime psi inverse q, because psi inverse is a diagonal matrix, so prime of transpose of a diagonal matrix would again be a diagonal matrix. So I have q prime psi inverse q again. Okay, and okay, so this is a symmetric matrix already. Now if I want to impose constraints, what do I have? It's a symmetric matrix and I'm imposing it to be a diagonal matrix. So diagonal is anyway nothing that we can control. So this part I can force to make it 0. This part would then automatically be 0. So how many entries here? So 1, or maybe if I go this way, so k minus 1 entries in the first row, k minus 2 entries in the second row, and so on up to 1 entry or 0 entry actually in the last row. Okay, 1 entry in the second last row. So 1 plus 2 plus k minus 1. These are the entries which I am forcing to be 0. So it would be k minus 1 into k by 2. Total number of constraints that I am putting would be k minus 1 into k by 2. Okay, so how many free parameters do I have? Okay, free parameters which would be equivalent to degrees of freedom. So degrees of freedom in a new model, or basically in an orthogonal factor model, would be pk we need from q plus p coming from psi. These were the original number of parameters, but now we are putting constraints, so some parameters would reduce, k into k minus 1 by 2. Okay, pk plus p minus this. So what would it be? It would be pk plus p. Okay, right now let me not simplify this. Right now let it be like this. Now finally what we are interested in is checking whether I have an exact solution or approximate solution or infinitely many solutions. Approximate solution would be in a scenario when I have no exact solution. Okay, so we define D as number of parameters in the original model. In the original model means no factor, complete data. In the original model, that is no factors, original variables, minus number of parameters in a new, that is orthogonal factor model. Okay, so in the original model we saw initially that I need to estimate sigma. Okay, see here. So when I estimate sigma, I am supposed to estimate p into p plus 1 by 2 parameters. This is the number of parameters in original model. So I have, yeah, so p into p plus 1 by 2 minus, in the new model I have pk plus p minus k into k minus 1 by 2. This is coming from here. Okay, so now let me try to simplify and see if I can get a slightly better form. So I have p square plus p upon 2 minus, so let this bracket be as it is. Let me simplify the inside things first. So this will be 2pk plus p minus k square plus k. Am I right? This would be minus k, and then with this minus sign it would become plus k. Okay, so this is p square plus p minus 2pk. I'm sorry, here I need to have 2p. Okay, so minus 2p minus k plus k square minus k. Okay, divided by 2. So this would be, let me try to pick terms which could be combined. So p square minus 2pk plus k square, then p minus 2p will become minus p minus k divided by 2. So this is, first three terms are basically p minus k whole square minus p plus k, and whole thing divided by 2. Okay, so I have p minus k whole square minus p plus k whole thing divided by 2 as the degrees of freedom, okay, for a model with k factors. Okay, so degrees of freedom, or the free number of parameters that need to be decided newly, freely, is degrees of freedom for a model with k factors is this, p minus k whole square minus p plus k by 2. Now how does this affect my analysis, or how does this affect my conclusions? If you recall, in linear algebra, when you are trying to discuss solutions of simultaneous equations, we had some constraints on the ranks of the matrices. So if your number of equations is exactly same as number of variables, number of linearly independent equations to be precise, so number of linearly independent equations is exactly same as the number of variables, then you would get a unique solution. Okay, if you have more number of equations than the number of variables, then what happens? And if you have less number of equations than the number of variables, then what happens? Okay, so you know, so we have exactly similar or parallel scenarios here. So let me introduce them. So I have three cases: d less than 0, d equal to 0, and d greater than 0. Okay, so what happens in each of these cases? So if d is less than 0, that means that degrees of freedom are negative. It would mean that the number of factors is too large. Okay, number of factors is too large relative to the number of parameters, and you may not have, you don't have enough number of variables to estimate so many factors. Okay, and this actually defeats the purpose. We were trying to do this for dimension reduction, hence this case is generally not of interest to us, and anyway there are infinitely many solutions, so picking the right one would become a trouble. Okay, so there are infinitely many solutions and the case is of no interest to us. Okay, if d is equal to 0 means number of parameters is exactly equal in both the setups, so you get unique solution, because this is just like a linear transform. Okay, so you get unique solutions. But in most of the times you are not interested even in this, because your primary aim is dimension reduction. So we want a setup where we are having less number of parameters in the new model. So the case which is of most interest to us is this, d greater than 0, where actually there is no solution. Okay, however, you can find an approximate solution. Okay, you can find an approximate solution, and of course you can rotate those solutions. Okay, so this is a case which is of most interest to us. By the way, even here when I mean unique solution, this is called as unique up to rotation. What do I mean by unique up to rotation? By rotating, I can still get multiple solutions like we discussed yesterday, but those solutions will be rotated versions of each other. They are not completely independently new solutions. Whereas here, when we say infinitely many solutions, they are independent of each other. They are not even rotated versions of each other. Got the difference? Okay, so as I said, we will mostly be interested in the case when d is greater than 0. That is, there is no solution, but we will try to find an approximate solution, and then we can rotate that approximate solution if needed for interpretation. Okay, so this is the basic concept of degrees of freedom in factor analysis. Let me take two small examples where we can do the actual calculations to see how this degrees of freedom concept can be used. Actually, degrees of freedom gives us an upper bound on number of factors that can be meaningfully extracted. Okay, for example, if I have p equal to 4, let's say, okay, then for p equal to 4, if I try to get k equal to 2, means if I try to get two factors, then what do I have? I'll have 4 minus 2 whole square minus 4 plus 2 by 2, correct? P minus k whole square minus p plus k by 2. So this would become 4 minus 6 by 2, so this is minus 1. So we are in the scenario where we have infinitely many solutions and this is not advisable. So in a 4 variable data, I should not go even for two factors. I should restrict myself to one factor. With one factor I would have 4 minus 1 square, 4 plus 1. So I would have 9 minus 5 by 2, which is 2, correct? So I can go for one factor model in 4 variate data, but I should not generally go for two factor model. See, when you go for actual analysis, you can get 2 factor, 3 factor, 4 factor models also, but ideally it is not recommended if your main aim is dimension reduction. Okay, now as I said, let us try to take a couple of small examples. So suppose I have p equal to 3, means I have 3 variate data, and k equal to 1, that is I am trying to identify one factor. What would be d in this case? It would be 3 minus 1 whole square minus 3 plus 1 divided by 2. So 4 minus 4 by 2. So basically 0. So d equal to 0, we know we are supposed to get a unique solution up to rotation. Okay. So let us try to introduce some notations. Suppose my original sigma matrix is sigma 1 1, 1 2, 1 3, 2 1, 2 2, 2 3. Of course, we know that sigma 2 1 is same as sigma 1 2. 3 1, 3 2, 3 3. Okay. And now I need only one factor. So my Q will be of order P cross K. So 3 cross 1. So let me call it Q1, Q2, Q3. And psi would be of order 3 cross 3. So psi 1 1, psi 2 2, psi 3 3, and the other entries are 0 because psi is a diagonal matrix. Okay. So can I actually try to get sigma as, let us assume we know actual sigma, so we don't need hat, as QQ plus psi. Means, can I actually find values of Q and psi to satisfy this equation? So let us try to write sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, 3 1, 3 2, 3 3. Okay. My Q is Q1, Q2, Q3. Then I have Q1, Q2, Q3 plus psi 1 1, psi 2 2, psi 3 3, 0 0 0 0 0 0. Okay. So let us try to simplify the right hand side. Left hand side is anyway a single matrix. So this would be Q1 square, then Q1 Q2, Q1 Q3, Q1 Q2, Q2 square, Q2 Q3, Q1 Q3, Q2 Q3, Q2 square plus psi 1 1 0 0, psi 2 2, and psi 3 3. Okay. Now, okay, let me write down sigma here so that we don't lose track. So sigma 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. See, coincidentally, Q1, Q2, Q1, Q2. So the symmetry aspect is taken care of. I don't need to worry about it. Okay. Now, because you know Q prime Q is symmetric. It's not magic. Okay, Q prime Q is symmetric. So yes, symmetry aspect is taken care of. Now, if I equate both the sides, what I get is sigma 1 1 equal to Q1 square plus psi 1 1. Sigma 2 2 equal to Q2 square plus psi 2 2. And sigma 3 3 equal to Q3 square plus psi 3 3. Correct? Then I have sigma 1 2 as Q1 Q2, sigma 1 3 as Q1 Q3, and sigma 2 3 as Q2 Q3. Correct? Q2 Q3. Do I need to put any other equalities? No, I think we have covered all the entries of sigma matrix because of symmetry. So I have only 6 equations, and then actually how many unknowns? 6 unknowns. Q1, Q2, Q3, psi 1 1, psi 2 2, psi 3 3. So I am expected to get unique solutions. Of course, these are not linear equations, but still. So can I do something to get a solution? Okay, so this first one seems a bit complicated because all the 6 parameters are involved there. Let us look at this second row. From this row, I can see that sigma 1 2, sigma 1 3, sigma 2 3, everything have something in common. So if I do sigma 1 2 upon sigma 1 3, what do I get? I will get q2 upon q3, and I know something here about q2 into q3. Okay, so can I use it somehow? Another thing that I can do is sigma 1 2 into sigma 2 3 is q1 square q2 q3. So basically sigma 1 2 sigma 1 3 is q1 square, and q2 q3 we know is sigma 2 3. Okay, so now I get something about q1 square. So I get q1 square as sigma 1 2 sigma 1 3 upon sigma 2 3. Okay, this is interesting because now I have got q in terms of sigma, and sigma is supposed to be known, or it can be estimated from the data. Okay, so I can get q1. Similarly, you can find out that q2 square would be sigma 1 2 sigma 2 3 upon sigma 1 3, and q3 square is q3 square will be homework. Okay, it's very easy, you can guess right now, but by the way, this also you are supposed to work out as homework. Okay, I mean, I have written direct answer, but you can find out. So now I know q1 square, q2 square and q3 square, and can I use that for getting psi 1 1, psi 2 2, psi 3 3 now? Yes, because I have this another set of equations, right? Sigma 1 1 equal to what? Sigma 2 2 equal to what? So I can write psi 1 1 as sigma 1 1 minus q1 square, psi 2 2 as sigma 2 2 minus q2 square, and psi 3 3 as sigma 3 3 minus q3 square. So now I have solutions. I have values of all the 6 parameters. Hence, I have gotten a unique solution. Okay. But of course, we said this is going to be unique up to rotation. So this is not completely unique. So up to rotation means my current loadings are q1, q2, q3. So because it's a 3 cross 1 matrix, my rotation options are limited. I can rotate by -1. So minus q1, minus q2, minus q3. This, let me call it say q1. If this is my original matrix q, then q1 is also a set of possible loadings. Okay, so this is rotation. So we have considered a case where I have 3 variables and we have tried to identify one factor from it. In this scenario, d is 0, so we could get a unique solution. Okay, so we could actually have 1-1 relationship between parameters of sigma, I mean elements of sigma and elements of the loading matrix and the specific variance matrix. Okay, however, as we said that we generally prefer other cases, so let me consider one more case also. So p equal to 2, k equal to 1. So in this case, d would actually be negative. So we need to see how there are infinitely many solutions, because we saw that in d less than 0 case, we claimed there would be infinitely many solutions. So for the sake of simplicity, let me deal with standardized variables. So I'll have one row 1 as sigma instead of sigma 1 1, sigma 1 2. Sigma 1 1, sigma 1 2 is also fine, but this would simplify our work. So this is, I need to express this as q1 q2 into q1 q2 plus psi 1 1 psi 2 2 0 0. I am following exactly the same steps that we did in the earlier example, just that because now I have only 2 variables, my Q matrix is of order 2 cross 1 instead of 3 cross 1. Okay, so I'll have q1 square plus psi 1 1, then q1 q2, q1 q2 and q2 square plus psi 2 2. okay, as this. Now what do I get if I try to find solutions? What do I get? So let me take q1 equal to some alpha, then q2 can be taken as rho by alpha because q1 into q2 is rho, okay. And does it satisfy the other equations? Psi11 would then become 1 minus alpha square and psi22 would become 1 minus rho by alpha whole square, okay. And this works for every alpha, okay. Of course we can put condition on alpha, so we can put condition that alpha is less than 1 and maybe alpha is positive. This we can put to make sure that psi11 is positive, that the specific variance is positive, okay. Here I would need a condition that alpha is less than rho also, so not just 1, alpha should be less than rho, because then only the specific variances would be positive. But technically even for alpha greater than rho, this is still a solution. It's not a solution that you would like to have because you want specific variances to be variances and hence positive, but yes, it is still technically a solution, okay. And as we change alpha we get many solutions, so we have infinitely many solutions. Now by the way, this brings me to another important point. When you are analyzing real data, it is possible to get estimates of specific variances to be negative. Let me repeat. When you are analyzing a real data set, it is possible to get estimates of specific variances to be negative, because specific variances we are obtaining by subtracting the relevant entries of sigma and qq prime, correct. So sometimes you may get estimate of specific variance to be negative because of the mathematical formulation, even though statistically it makes no sense, okay. But mathematically it is possible, and that is why there is a special name for it. It is known as Haywood case, okay. So Haywood case is a scenario where you get specific variances to be negative, which ideally you don't want. You want specific variances to be positive, but yes, mathematically you can get it. And there are different ways. Some people keep it as it is, some people force those to 0 at least instead of keeping them negative, okay. So we started with computation of degrees of freedom for factor model, and we saw two scenarios where you can find either you can find an exact or infinite number of solutions, okay. The approximate solution case we did not discuss because approximations would need some methods, okay. So in the next lecture we would discuss the estimation in factor model, where we will discuss this scenario where approximate solutions exist and exact solutions don't exist. Let me stop here. Thank you.